Ladies and gentlemen, for over a century, the electric motor was treated as a finished invention, a solved problem locked in textbooks and factories around the world. But what if that assumption was wrong? What if the motor powering the future wasn't just improved but completely rethought? Designed not as a standalone machine but as the heartbeat of an intelligent connected system. Today we're diving into how Tesla took a technology the world thought it understood and transformed it into a platform for efficiency, performance, and scale, reshaping not just how vehicles move but how energy itself is used. And Tesla set out to rethink the electric motor not as a single component, but as part of an integrated system where efficiency, scalability, and real-world performance matter more than tradition. From the beginning, the focus was never on reinventing physics but on re-engineering how known principles are applied, manufactured, and optimized at scale. The electric motor became a platform for innovation rather than a finished product, evolving alongside power electronics, software, battery chemistry, and vehicle architecture. And traditional electric motors were often designed for industrial use, prioritizing durability over efficiency, and built with assumptions that did not translate well to mass-market vehicles. Tesla challenged those assumptions by designing motors specifically for automotive applications where weight, energy density, thermal behavior, and cost per unit are critical. This led to a deep exploration of motor topologies, materials, and control strategies, resulting in designs that balance performance with manufacturability. And one of the most significant shifts was the emphasis on system-level efficiency. Instead of optimizing the motor in isolation, Tesla engineered the motor, inverter, and gearbox as a tightly integrated drive unit. This allowed losses to be minimized across the entire system, rather than shifted from one component to another. Advanced power electronics enable precise control of electromagnetic fields, improving torque delivery, while reducing waste heat. Software plays a central role, continuously adjusting motor behavior in real time based on driving conditions, temperature, and efficiency targets. And material science also became a key lever for innovation. Tesla examined how copper, steel, and magnetic materials could be used more effectively, reducing reliance on rare elements while maintaining high power density. The rotor and stator designs were refined to improve magnetic flux paths and reduce energy losses, allowing motors to deliver high torque without excessive size or weight. These improvements translated directly into longer range, faster acceleration, and improved reliability, and manufacturing was treated as a core part of the engineering challenge. Tesla redesigned motors to be simpler to assemble with fewer parts and tighter tolerances that could be achieved through advanced automation. By aligning motor design with high-volume production techniques, costs were reduced without compromising performance. This manufacturing-first mindset allowed rapid iteration where design improvements could be tested, validated, and deployed at scale in shorter timeframes. And thermal management emerged as another area where Tesla redefined expectations. Electric motors operate most efficiently within specific temperature ranges, and pushing performance without managing heat leads to degradation and loss of efficiency. Tesla integrated advanced cooling strategies directly into motor design, ensuring consistent performance under sustained high loads. This made it possible to deliver both everyday efficiency and extreme performance without trade-offs. And Tesla also embraced continuous improvement rather than fixed design cycles. Motors are not treated as static components, but as evolving systems that benefit from data collected across millions of miles of real-world use. Insights from vehicle operation feedback into design refinements, control algorithms, and manufacturing processes. This feedback loop allows incremental gains that compound over time, steadily improving efficiency, durability, and performance. And perhaps most importantly, Tesla reframed the role of the electric motor in the broader mission of sustainable energy. By making motors more efficient and affordable, energy consumption is reduced not just at the vehicle level, but across the entire life cycle of transportation. Every efficiency gain translates into fewer batteries required, lower material usage, and a smaller environmental footprint. And in reinventing the electric motor, Tesla demonstrated that meaningful innovation often comes from questioning long-held assumptions, integrating disciplines that were once separate, and aligning engineering decisions with large-scale impact. The result is not a single breakthrough but a continuously evolving motor platform, designed to support a future where electric transportation is the default, not the exception. And this platform mindset enabled Tesla to explore motor designs that could be tailored to different use cases without reinventing the entire system each time. By adapting winding configurations, cooling paths, and control software, the same foundational motor architecture could support everything from high-efficiency daily driving to high-performance applications. This flexibility reduced complexity across the product lineup, while preserving a consistent engineering philosophy centered on efficiency and scalability. And another critical advancement was the close coupling between the motor and software intelligence. Rather than treating control algorithms as a fixed layer, Tesla designed software as an active participant in motor performance. Real-time monitoring of current voltage, temperature, and load allows the motor to operate closer to its optimal limits without sacrificing longevity. This approach unlocks performance that would otherwise require larger or heavier hardware, proving that intelligence can substitute for excess material. And Tesla also re-examined how motors behave under real-world conditions rather than ideal laboratory scenarios. Stop-and-go traffic, rapid acceleration, regenerative braking, and varying climates place complex demands on an electric motor. By designing with these realities in mind, Tesla ensured that efficiency gains translate into meaningful benefits for drivers. Regenerative braking in particular was refined to seamlessly integrate motor behavior with energy recovery, turning deceleration into an opportunity rather than a loss. And the pursuit of efficiency extended beyond peak performance metrics and into everyday operation. Motors were optimized to spend more time operating in their most efficient zones during typical driving patterns. This required a deep understanding of how drivers use vehicles and how energy flows through the system over time. The result is improved range without increasing battery size, a critical factor in reducing cost and resource consumption. And Tesla's approach also challenged the idea that electric motors must rely heavily on rare or expensive materials to achieve high performance. By carefully balancing electromagnetic design and control strategies, the company reduced dependence on constrained resources while maintaining competitive power output. This decision was driven not only by cost considerations, but by the need for long-term scalability as electric vehicles moved toward global adoption. And durability and reliability were treated as performance metrics in their own right. Motors were engineered to maintain efficiency over hundreds of thousands of miles, resisting wear, thermal cycling, and environmental stress. This focus reduced maintenance requirements and increased confidence in electric powertrains as a long-term solution. The simplicity of the motor combined with advanced monitoring allows potential issues to be identified early, further extending service life. And integration with the broader vehicle architecture amplified these gains. The motor does not operate in isolation, but as part of a tightly coordinated system that includes the battery, power electronics, and chassis. By aligning these elements, Tesla minimized energy losses and improved responsiveness. The result is a driving experience that feels both effortless and precise, reinforcing the advantages of electric propulsion. And Tesla also leveraged vertical integration to accelerate innovation. By controlling design, manufacturing, and software development under one roof, improvements could be implemented rapidly without waiting for external suppliers to adapt. This allowed faster experimentation with new motor configurations, cooling techniques, and control strategies, turning iteration speed into a competitive advantage. And the data-driven nature of this process cannot be overstated. Every vehicle on the road contributes insights into how motors perform over time and across conditions. This information feeds back into simulation models and design decisions, enabling continuous refinement. Small efficiency improvements, when applied across millions of vehicles, result in substantial energy savings at a global scale. And by redefining the electric motor as a living system, rather than a static component, Tesla transformed a mature technology into a source of ongoing innovation. The motor became a catalyst for progress across efficiency, cost, performance, and sustainability. This reinvention did not rely on a single invention, but on a disciplined commitment to integration, iteration, and impact, reshaping expectations for what electric propulsion can achieve in the real world. And this philosophy also influenced how Tesla approached validation and testing. Instead of relying solely on standardized benchmarks, motors were subjected to extreme scenarios that mirror real customer use over many years. High-load acceleration cycles, prolonged highway driving, repeated fast charging, and harsh environmental exposure were all treated as design inputs rather than edge cases. By designing for these extremes, the motors deliver consistent performance in everyday conditions with significant margins of reliability. And noise, vibration, and harshness were addressed as part of motor innovation, rather than secondary refinements. Electric motors can reveal subtle imperfections that are masked in combustion systems, making precision essential. Tesla refined electromagnetic balance rotor geometry and control waveforms to reduce acoustic noise and vibration at the source. This resulted in quieter operation and a smoother driving experience without adding insulating materials or mechanical complexity. And another area of reinvention was the relationship between efficiency and performance. Traditionally, high power output came at the cost of efficiency, especially under sustained load. Tesla challenged this trade-off by designing motors that maintain high efficiency across a wide operating range. This allows vehicles to deliver rapid acceleration when needed while remaining energy efficient during cruising. The ability to seamlessly transition between these modes is driven by precise control of electromagnetic forces and real-time software optimization. And the modularity of motor components also played a role in accelerating innovation. By standardizing certain interfaces while allowing internal variation, Tesla enabled faster upgrades and experimentation. Improvements in materials, winding techniques, or cooling methods could be introduced without redesigning the entire drive unit. This modular approach reduced development time and allowed proven advancements to propagate quickly across different vehicle platforms. And Tesla's motor strategy also aligned closely with its approach to energy recovery. Regenerative braking was treated as a core function rather than a supplemental feature. By optimizing how the motor transitions between driving and energy recovery modes, Tesla maximized the amount of energy returned to the battery during deceleration. This not only improves range but also reduces wear on traditional braking components, further enhancing system efficiency and longevity. And supply chain resilience became an integral consideration in motor design. By minimizing reliance on scarce materials and simplifying manufacturing steps, Tesla reduced vulnerability to external constraints. This approach supports long-term scalability and ensures that motor production can expand rapidly as demand grows. Design choices were evaluated not just on technical merit, but on their ability to support global manufacturing at unprecedented volumes. And the learning curve associated with this scale of production became a strategic asset. As manufacturing volumes increased, process improvements led to tighter tolerances, higher yields, and lower costs. These gains fed back into design decisions, enabling further simplification and optimization. The result is a virtuous cycle where manufacturing excellence drives engineering progress, and engineering progress simplifies manufacturing. And Tesla also considered how motors interact with the broader energy ecosystem. Efficient motors reduce overall energy demand, making it easier to integrate renewable energy sources into transportation. Lower energy consumption per mile translates into less strain on charging infrastructure and electrical grids. This system-level perspective reinforces the role of motor innovation in enabling a sustainable energy future beyond individual vehicles. And continuous software updates further extend the life and performance of the motor system. Improvements in control algorithms can unlock additional efficiency or refine torque delivery without physical changes. This capability transforms the motor into an upgradable component where performance can improve over time rather than degrade. Customers benefit from advancements that were not even envisioned at the time of purchase. And the cumulative impact of these decisions is a motor that reflects a fundamentally different approach to engineering. It is not defined by a single specification or breakthrough, but by how seamlessly it integrates efficiency, performance, manufacturability, and scalability. Every design choice is evaluated through the lens of long-term impact, ensuring that progress compounds rather than plateaus. And by treating the electric motor as a cornerstone of system innovation, Tesla elevated it from a commodity component to a strategic differentiator. This reinvention continues to evolve as new materials, algorithms, and manufacturing techniques emerge, reinforcing the idea that even the most established technologies can be transformed when approached with first principles thinking and an uncompromising focus on real-world impact. And this way of thinking encouraged constant reevaluation of assumptions that had long guided electric motor design. Instead of accepting industry norms around size, weight, and operating limits, Tesla repeatedly asked whether those limits were real or simply inherited from older technologies. This questioning led to motors that deliver more power from less material, challenging the idea that higher performance must always mean larger components. And as vehicle architectures evolved, motor placement and packaging were optimized to support better weight distribution and vehicle dynamics. Compact drive units allowed more freedom in chassis design, improving handling and safety without sacrificing interior space. The motor became an enabler of better vehicle balance, rather than a constraint that dictated layout. This integration reinforced the idea that motor design influences every aspect of the vehicle, from driving feel to structural efficiency. And Tesla also invested heavily in simulation and digital modeling to accelerate motor development. Advanced electromagnetic thermal and mechanical simulations allowed engineers to explore thousands of design variations before physical prototypes were built. This reduced development time while increasing confidence in performance outcomes. Simulation was not treated as a replacement for testing, but as a force multiplier that made testing more targeted and effective. And the role of automation in motor production continued to expand. Precision winding, automated assembly, and inline quality inspection ensured consistency at high volumes. Automation reduced variability, which is critical for achieving tight efficiency targets across millions of units. By designing motors that are compatible with automated processes, Tesla ensured that quality improves as production scales, rather than degrading under volume pressure. And energy efficiency gains at the motor level had cascading effects throughout the vehicle. Smaller, lighter motors reduced the load on batteries, allowing for optimized pack sizes and improved thermal management. This interplay between motor and battery design highlights how efficiency improvements compound across the system. Each gain unlocks further opportunities for optimization, creating a chain reaction of benefits. And Tesla's approach also prioritized adaptability to future technologies. Motors were designed with enough flexibility to accommodate advancements in power electronics, battery voltage, and charging capabilities. This forward-looking design philosophy reduces the need for complete redesigns as other systems evolve. The motor remains compatible with next-generation platforms, extending its relevance and value over time. And another defining aspect was the focus on consistency of performance. Rather than optimizing for peak numbers that are rarely used, Tesla emphasized sustained output that drivers can rely on repeatedly. This meant designing motors that can deliver strong performance lap after lap, mile after mile, without thermal degradation. Consistency became a hallmark of quality, reinforcing trust in electric propulsion. And Tesla also recognized that motor innovation has implications beyond passenger vehicles. The same principles of efficiency, durability, and scalability apply to energy storage, industrial applications, and future transportation systems. Lessons learned from vehicle motors informed broader energy solutions, creating cross-domain benefits that extend the impact of each innovation. And the emphasis on real-world data continued to shape refinements long after vehicles reached customers. Performance metrics, efficiency trends, and component health indicators were analyzed continuously. This feedback informed subtle adjustments in control strategies and design parameters, allowing motors to improve quietly over time. Innovation became incremental yet relentless, driven by evidence rather than speculation. And thermal integration across systems reached new levels of sophistication. Motors, inverters, and batteries share thermal resources to maintain optimal operating conditions with minimal energy expenditure. Waste heat is managed intelligently, improving overall system efficiency. This holistic thermal strategy reflects a deep understanding of how interconnected components influence one another. And Tesla's motor reinvention also influenced perceptions of electric vehicles. Smooth acceleration, quiet operation, and immediate torque changed expectations of what a car can feel like. The motor was no longer an invisible component, but a defining element of the driving experience. This emotional connection reinforced adoption by demonstrating that sustainability and performance are not mutually exclusive. And at the manufacturing scale required for global adoption, even small efficiency improvements matter. A fraction of a percent gain multiplied across millions of vehicles results in substantial energy savings. Tesla's willingness to pursue these incremental gains reflects a long-term mindset where progress is measured in cumulative impact rather than singular breakthroughs. And by embedding this philosophy into motor development, Tesla ensured that innovation remains continuous rather than episodic. Each generation builds on the last, informed by data, manufacturing experience, and evolving system requirements. The electric motor, once considered a solved problem, continues to reveal new opportunities for refinement, when examined through the lens of integration scalability and real-world performance.